So I ask you to predict the freezing point of this substance in water. You need to get delta TF. And so that's equal to KF times molality times I. So if I just tell you what the substances are, you can actually get KF because that depends on water. And for water, KF is 1.86. And you can also get I if you know the identity of the solute. How do I get I? What should I be? In this case, it should be 4 because when one of these breaks apart, I get 3 Na pluses and 1 PO4 minus 3. So a total of 4 particles. And I can predict that because I know Na should have a +1 charge to have the same number of electrons as a noble gas. And if there are 3 of them there, then those 3 positives are going to separate. And if I have 3 positives, the PO4 must have a 3 negative if it was neutral to begin with. And phosphorus and oxygen are not likely to break apart because they're sharing electrons. Right? The metal interaction with nonmetals is ionic. That will break when I put it in water. The charges will separate, get surrounded by water molecules. But the interaction between nonmetals, the phosphorus and the oxygen are both nonmetals, they will need to stay connected because they're sharing electrons to make their noble gas configurations. If they break up, they won't have their noble gas configurations anymore. We don't break covalent bonds during dissolving. We only break ionic bonds and intermolecular attractions when we dissolve something. So since for every one of these I expect to get 3 plus 1, 4 total particles, I should be 4. But that's an estimate. Because when I actually dissolve it, some of the ions might pair up and I might not get a full expected 4 number of ions separated. I might have less than that. But if I don't know how many are actually breaking apart, the best I can do is estimate it. And then to get M, I would need to have some information about the quantity of the solute and the quantity of the water. I would give you either grams of the solute. I would probably give you the grams of the solute because that's the way you'd measure it in lab. And you'd use the molar mass to convert it to moles, right? So you'd convert any quantity I give of the solute into moles of the solute. And then to get molality, you need moles, you need that number. You need to get that, and you need to divide it by the kilograms of water. So if I give you a quantity of water in grams, you convert it to kilograms. If I give you a quantity of water in milliliters, I'd have to give you the density to convert it to grams so that you can convert it to kilograms. We need kilograms if we're working with molality. So we plug those numbers in and divide. And so let's just say you did that and the molality came out to be 0.40. I might also just be nice and give you the molality. Probably not. So you plug in the molality and you calculate delta T. 1.86 times 0.4 times 4 gives me 2.976, and that's a change in temperature, so it'll be in degrees Celsius. So I know it's freezing, so I know it's going down from the normal temperature at which this liquid freezes, and since for water that's 0, I know the freezing point is going to be negative 3 degrees Celsius. And I'm limiting here to 1 sig fig because this is an estimate. I don't have a lot of certainty in that. I really only have one significant figure of certainty. I can't say it's 4.0 because really I don't know. It might be 3.7 or 3.4 or even, maybe it should actually be 3 instead of 4. I don't even have a lot of certainty in that one digit. So I definitely don't have 2 digits of certainty. So I've got 1 sig fig here. Yes?
Would that be the freezing point or the change in freezing point?
It's the change in freezing point, but it's also the freezing point because the normal freezing point of water happens to be 0. if I was working with a different solvent, I would have to subtract that value from whatever the normal freezing point for that solvent happened to be to get the actual freezing, which I did because water is 0.